I'm going to go over a little bit some of the material I covered last time because I had a sense I was looking at a lot of blank faces, and I want to make sure that you get the gist of what's going on. So one of the main topics we were talking about last time was the idea of how it is we control our navigation. How do we know where we're headed? How do we know if we're on the right track or if we're on the wrong track? And the first hypothesis to address this was by Gibson, and he proposed that the focus of expansion provides information about where we're heading. Now, there's a problem with this proposal, and that is it works fine if our eyes are stationary. So if our eyes are stationary and I'm walking toward you, the focus of expansion is at the place where I'm heading, which would be emanating from you. But if we're moving our eyes, all bets are off. This idea just doesn't work anymore. So here's the idea. If our eyes are stationary and we're traveling toward this post, you see how all these vectors point toward the post? All right? And so in this case, the focus of expansion, so everything's emanating from here. And that's telling us we're heading toward the post. However, if we move our eyes, so let's say we're tracking a dot in a stationary environment, then all the points in the visual field are going to move opposite to the direction that we're moving our eyes. All right, so if I move my eyes to the right, then everything in the visual field is going to move to the left. And if you combine those two things, so now I'm traveling through the environment toward this post, but I'm also moving my eyes at the same time. Say I'm tracking this dot. Now, whatever you're tracking is going to be the focus of expansion. And so in this case, the focus of expansion isn't telling you about where you're heading anymore. And Gibson's original hypothesis won't work. So how do we solve that? Well, first of all, Warren and Hannon did an experiment that showed we really can solve that. So what they did is they compared two conditions, one where you're moving through a flow field that looks like this, and observers have to judge whether they're moving to the left or right of the post. And the other is they showed them a flow field looks like this, where they're actually moving their eyes while they're making that judgment. So they're tracking a point on the screen. And they compared the accuracy of the judgments, and lo and behold, what they found is observers are pretty much equal at judging the direction they're heading, whether their eyes are moving or whether their eyes aren't moving. So what that means is that there must be some way of separating out the motion of our body towards some point that we're heading toward and the motion of our eyes. And so the question is, how can we do that separation? Now, there are three models that I talked about last time. One of them involves extraretinal signals. So the idea here is that when I'm moving my eyes, I send command to the eye muscles to change the position of the eyeball in its socket. And when I do that, the command that goes to the muscles is also feeding into our perceptual apparatus. All right, so the muscle commands are telling us about the nature of our eye movements. And we could use those commands in principle in order to separate out the two components. Now remember, I told you about a couple of experiments, one where the guy went on a curare drip where he's sending commands to the muscles, but there's no movement, and he sees the world move in the opposite direction. The other example of this is when you press on your eyeball and make your eye move artificially, and the world looks like it's moving. That's another example. The eyes are moving in that case, but you're not generating commands to the eye muscles to make it happen. So this is one model. Second model involves differential invariance, and I'm not going to go into what that means today. The key thing about this one is it only works on smooth surfaces. So if I'm traveling over a ground plane, you could in principle use this model. But if you're traveling through a forest, for example, it wouldn't work, or a cloud of dots. It only works on smooth surfaces. And the third model involves motion parallax. So that's when you have points at different depth and you move your head back and forth and you see them move at your fingers move at different velocities. That's called motion parallax. You can also exploit that in order to separate your motions of your body from the motions of your eye. So we've got these three models. And what Warren and Hanna did was a series of experiments to try and figure out which of these, if any, are what observers use in order to make judgments when they're moving their eyes while traveling through space. So the first experiment they did was designed to test this one. All right? So extraretinal signals are only good if you're sending commands to your eye muscles. All right, so in his experiment where subjects are tracking a point, the subjects are doing that, right? They're actually moving their eyes. But suppose that you just modified the flow field so you get exactly the same flow field you would if you were moving your eyes, but you don't move your eyes. You keep your eyes fixed, but you get the same flow field that you would get if you were moving your eyes. If you're using extraretinal signals, that should screw you up big time. But what Warren and Hanna found is that it doesn't. So here's a comparison between moving your eyes while looking at a flow pattern or looking at a flow pattern with a simulated eye movement where you're not moving your eyes, and there's not much difference. And so the interpretation of that is that extraretinal signals are not a necessary condition in order to accurately judge heading when you're moving your eyes. The next one they did was to try and knock out the differential invariance, and they did that by having subjects move through a cloud of dots. So this is what that looks like if your eyes are stationary. Here's what it looks like if your eyes are moving, and you see a lot of these vectors are crossing one another. That's the motion parallax. What they found was, in this condition, so here, because you're moving through a cloud of dots, the differential invariants aren't going to work anymore. They only work on smooth surfaces. But subjects do okay in this situation. And so again, if you compare the moving versus simulated eye movements, they're pretty much the same. Actually, the simulated eye movements do a little bit worse, but probably not statistically significant. So what this shows is that they can use differential invariance as a source of information. Now, in order to knock that out, remember, differential invariance only work, not differential invariance, motion parallax, right? Remember, motion parallax only works when you're looking at things of different depths, right? So if you take your fingers and you move your head back and forth, you'll see them move differently on the back of your eye. But if you put your fingers at the same depth, that doesn't happen. And so that's the way you try to knock out motion parallax. You have the subjects walking toward a flat wall that's covered with dots. And that looks like this while they're moving their eyes. So here's where they're headed. This is the dot they're tracking. And so as you see, the flow field emanates from the point that you're tracking. And what they found in this case was that if they're actually moving their eye, they do fine. But if they're looking at the simulated eye movement, they're completely at chance. All right, now what these results suggest is that there are two different methods we can use to solve this problem. If we've got motion parallax, we can use it. If we don't, we can use extraretinal signals. But if we don't have either of them in this condition, then we're screwed and our performance is a chance. All right, so just like we saw when we looked at nighttime vision versus daytime vision and the optimal way of designing a visual system to do that, and the visual system is actually designed to do both. So we have two visual systems essentially. We saw the same thing in shape from texture, right? We've got one mechanism that works when we've got lots of perspective, and we've got another mechanism that works when we have very little perspective. So navigation is a pretty important function for mobile animals. And it's probably not surprising that we have multiple mechanisms to take care of that. All right, so this is the key slide. You take away the motion parallax, subjects are a chance if they have a simulated eye movement, but if they're actually really moving their eyes, then they do just fine. So this is what indicates they can use either motion parallax or extraretinal signals. Any questions about this before I move on? All right, let's move on then. And last time at the end of class, I started talking about what I called the perception action cycle. That's the idea that we have if I'm navigating through the world, like suppose I'm walking toward you and I veer off to the right and the focus of expansion is over here and I go, no, I want to walk toward you. I change my direction of heading, but I may overcompensate and walk in this direction instead. So we're constantly adjusting our motions our body motions based on the feedback that we're getting from visual input. So the idea is the pattern of flow causes us to make a motor response. I want to walk toward him, I see I'm moving in the wrong direction, I correct my behavior. That also changes the pattern of optic flow, and it tells me whether my correction is getting me to the place I want to go, or tells me I have to correct some more, or correct in the opposite way, or something like that. Now, one of the most basic aspects of this correction that you don't think about, what's unique about humans over most other animals? Well, there are lots of things that are unique about humans, but one of them that very few animals have is we walk on two legs. Why do you think that's unusual in the animal kingdom? Anybody want to venture a guess? What do you think?
Not super efficient as you're running.
Well, it's very efficient. Efficiency is not the problem. It's not very stable. So ideally, what you would like, so the optimal configuration for animals, if you want stability, is to have 6 legs. Why do you think that is? Anybody want to venture a guess? Why 6 legs?
You can balance forward and back, side to side, on an angle.
Okay, so 2 legs aren't stable, but 3 are, right? So a tripod is always stable no matter what environment you put it on. If you have 6 legs, right, you plop down a tripod, and then you lift the other one up, plop it down, then you have a stable stance on the second tripod, you lift the first one up. So you're always standing on at least 3 entities that form a tripod. We don't have that when we're 2 legs, right? So basically you lift one up, you're balancing on one leg, you land on a single leg. So we spend most of our time when we're locomoting, not even on 2 legs, but on just 1 leg. Now, it's also a problem if we're not locomoting. So let's say we're just standing. Well, you've probably seen that. I'm sure you've all seen people who are drunk. And what do they look like when they're just standing still and they're drunk? All right, they may wobble a little bit like this. If you put a person on a force table while they're drunk, you can actually see it. The center of gravity moves back and forth and from side to side. However, if I put one of you on a force tablet and you haven't drunk anything at all, and you're just standing there and you're perfectly normal, turns out you sway back and forth and side to side too. It's just a much smaller amount than the drunken person does. Right? So the fact is that when we're just standing up, we are continuously falling down. So why don't we fall down? Well, we have a bunch of mechanisms, old biologically ancient mechanisms. In our ankles and joints is one that detect when we're falling forward or falling back. And there's also a visual component to that. So stand up for a second. All right, so if you were falling forward, what would you see?
I would just like.
Yeah, but what would be happening in your eyes in terms of the visual flow? So if you're falling forward, you get closer to me, right?
Yeah.
And when you get closer to me, then everything expands. Now suppose you're falling backward, so lean back a little bit, then everything recedes. You can sit down. All right? So when you're falling forward, there's this very subtle expansion of the visual field. And when you're falling backward, there's this very subtle compression of the visual field. And we detect that, and it's tied into our motor reflexes, and we correct for those. All right, so if we're falling forward, we correct and move backward a little bit. We're falling backward, we correct and move forward a little bit. So I want to introduce you to one of my favorite experiments of all time. It's by a friend of mine, a guy by the name of David Lee, and he teaches at Edinburgh University. I know for a fact that he's retired now, but he was very interested in this. And so he asked the following question. Suppose I had people standing in a room, and the floor is stable, but the room itself can move back and forth. All right? So I'll pick on you again. So let's stand up. We'll do the experiment. Right? So now you're in a room. You're just standing still. Right? Your eyes are detecting all these subtle flows. And suppose that the whole room, me included, all of a sudden move like this, including the chairs and everything around you did this. How would you interpret that?
Like the room is tilting up?
Well, you've all been in the situation, right, where you can sit down now, where you're in a car and the car next to you backs out and you think you're moving forward. Well, that feeling is even worse if the cars on both sides are backing out at the same time. And the wall in front of you is also expanding. All right? That's providing you with pretty compelling information that you're going forward. All right? So let's say you're standing in a room and everything moves to expand, and your brain is telling you, hey, I'm going forward and I don't want to. How's your body going to react? It'll compensate by moving backwards. And so what might happen? Since you're not actually falling forward when this occurs,
I fall back.
yeah, you might fall on your butt. Now, if you're an adult and you're sober, you wouldn't do that. But suppose you were a toddler. There's a reason we call toddlers toddlers. What is it? Where's the name toddler come from? Any guesses? It means they're not very stable. They're toddling. All right? They don't have particularly good balance. And so if you do this trick to a toddler, they'll fall over. Now, that's not so bad for a toddler because they fall all the time. You can see why this is my favorite experiment. All right, so here we have our toddler here. The room moves in this direction, and that's telling the toddler what? He's falling forward. I'm sorry, he's falling backward. And so what the toddler going to do? The toddler tries to correct. So that's what the room's telling it. The toddler tries to correct and falls on its face. Now I'm seeing grins here. Last time I did this class, I put up this slide and somebody in the back of the room said, "Do you got that on tape?" And I said, "Well, as a matter of fact, I do." So here's an example of the moving room. This is in the 1970s. You can see the hairdo there from a typical British 70s person. And that's a little toddler there. And let's see how the toddler behaves. You know, the mom's letting this happen. So this is Raleigh Lishman. He's waiting for the toddler to turn around. And now he moves the room and down goes the toddler. And see, the toddler's not particularly upset by this. Just to show it's a happy toddler. No worse for wear. All right, now when a toddler falls over, it's no big deal. When an adult falls over, it's, so this is Raleigh Lishman in the room, and it's moving, and he's pretty stable. He doesn't fall over. But now look what happens when we stick him up on this board where the balance is a little more tenuous. So if his eyes are closed, he can't balance. He needs that visual information in order to balance on the board. But now if he's in the moving room, they're not going to show him. Not going to show him going down. So this is an absolutely fabulous example of the perception-action cycle. And it's also a good example of how a lot of this activity is taking place at really basic levels of the nervous system, right? So a lot of this stuff is happening in the spinal cord because balance is so important for us. Now, there's some interesting work on this stuff in robotics. The first robots would literally, they would have 6 legs and they'd walk on 2 tripods. But there's a guy, I've forgotten his name, he's at MIT, and he was trying to model human gait. And he said, well, the ultimate of this is suppose you only had 1 leg, right? So you're like this, and then, you know, you had to hop on 1 leg wherever you went. And the instability is magnified even more. And so they built this dynamic system where they had a number of sensors that detected whether the leg was falling, and well, the leg's always falling, so what direction it's falling. And they built in correction mechanisms. And if you watch, years ago I saw a film of this robot, and it really looked like it was alive, right? So it's standing there and it would fall and then it would correct in exactly the same way that a human would if they were trying to balance on 1 leg. And then the researchers would go and they'd kick the thing and make it fall over, and it would try to get up. But it really looked like a sentient animal because that's the way animals behave, except maybe animals that have 6 legs that are inherently more stable. But there's a lot of good reason why we only walk on 2 legs, because it frees our arms to do other stuff, like hold weapons and shoot things. All right, here's another experiment by Bill Warren that looks at this. This is a nightmare experiment. I visited his lab one time, and he had this giant treadmill. How many of you have run on a treadmill before? And when you get tired, what happens?
You start slowing down.
Yeah, you can't keep up with the treadmill, and you don't want to fall down on a treadmill. He had this huge treadmill. It was like 6 feet long and 5 feet wide. And at the end of the treadmill, there was this huge projection video screen. So you think it's hard enough to run on a treadmill normally. So these subjects are running on a treadmill, and they're looking at a pattern of optic flow while they're doing it. And so what he's trying to do is to see how the flow patterns modulate their gait when they're walking on the or running on the treadmill. And so I visited there, and he asked me you want to do this? And I looked at the treadmill, and I looked at this guy. I said, I don't think so. I'm not running on that thing. I like my limbs intact. So let me show you what this looks like. So here, it's showing the room swinging back and forth like so. And what they're doing is while the subject's running, they're measuring their center of gravity, and sure enough, the subjects sway using the flow. Now here the oscillation is fore and aft, and the subjects sway this way now. So that's the idea. The pattern of flow that you're looking at really does affect your center of motion. So even if you're running or just standing still, the optical flow pattern will change your stance, or it will change how your center of motion moves while you're locomoting. All right, let's do another experiment. I'm going to show you a video, and I want you to tell, well, let's do an experiment here. I think I've done this experiment before.
Yeah?
But, so what happened here? What happened?
He caught it.
I first threw it at him, right?
Threw it at him and then he caught it.
Did I tell him I was going to throw it at him?
No.
Why didn't you reach for it?
Because it was to him.
Right, so everybody in the class knew wasn't coming toward you. You didn't have to change your stance. Wasn't coming toward you. You could just look at him and laugh. But he knew if I don't get my hands up and catch that thing, it's going to hit me in the chest and the whole class will laugh at me. And I don't want that to happen. And so he caught it. Now the question is, how is it that he knew it was going to hit him and you two knew it wasn't going to hit you? That's the question. By the way, this is one of the most basic things. Little chicks or baby goats or baby sheep can do this within an hour of being born. They know if something's coming at them. And the way they do that experiment, by the way, is they put these baby animals on a table, and then they have a shadow projector, And you could have an expanding shadow, and if you do that, the baby goat will jump out of the way. If you have a receding shadow, the baby goat goes, meh. All right, so you got to tell me, is this thing going to hit you or not? How about this one? All right, the key here to knowing that it's going to hit you is that it's the focus of expansion. Though in this case, it's not the focus of expansion caused by your motion, it's the focus of expansion caused by the motion of this object. Now, but there's another problem here. It's not just that he knew that the laser pointer was hurtling towards his head. What else do you have to know? You had to catch it, right?
Yeah. When is it going to get there? When do I close my hands? How fast?
When is it going to get there? And so now the question on the floor is, how do you know when the thing's going to get there? Now you make these decisions all the time, right? You're in an intersection, cars coming down the road, and you have to decide, do I have time to cross the intersection before the car hits? Now, if I'm driving with my wife, her tolerance for this is a lot lower than mine is. So I cross and she goes, "What the hell are you doing?" And I say, "If you don't like my driving, drive yourself." That exchange has happened hundreds of times throughout our... So one way in principle that you could do this is you could calculate the speed that the object is traveling through the air. And you could also calculate the distance it is away from him at any particular moment in time. So if you know time to contact is distance divided by speed. So if you could calculate the speed of the object and you could calculate its distance, then you could figure out time to contact. However, it turns out we are really crappy at judging speed and we're really crappy at judging distance. So it's unlikely we do this. Now there's another model. This was first proposed by the same David Lee who built the moving room. Is that you can do this based solely on optical variables. So if you take time to contact, assuming that the object's traveling at a constant velocity, equals the angular size of the object divided by the rate of expansion. So both of these things are measurable on the retina. So you take how big it is in your visual field divided by how rapidly is the size changing. And if you divide those two quantities and do some simple calculus, you can show that that ratio equals time to contact. Now the first experiment on this was done by, as I said, that model was developed by David Lee in the late 1970s. And this experiment was done when I was I a graduate? Yeah, I was a postdoc back then. And I was really interested in David's work and tried to come up with a paradigm to study it. And so the way I did it was to, this is probably before your parents were born. The way I did it was, imagine you got two objects. You don't know how big they are. You don't know how fast they're moving, but you want to decide which one is going to hit you first. That's the task. There's no information about distance. There's no information about size. All you have is the optical motion. And here's what that looks like. So you got to tell me which one's going to hit you first, the one on the right or the one on the left? Left or right?
Left.
All right, now a couple of things to note about this. Notice the one on the left is smaller than the one on the right. I'll show it again just for you who weren't. So the way these are designed is that the smaller one would hit you first half the time, and the fastest one would hit you first half the time. So you can't use just the rate of expansion, and you can't just use the projected size. You had to use the ratio of the two. And I also terminated the display before it really got to you, because then the one that hit you first would always be the biggest one. And here's what the data look like. So this is the difference in time to collision in milliseconds. This is a percent correct. Threshold is usually defined at about 75%. And what that shows here is that we can detect a difference in time to contact of only 50 milliseconds. Phones away, please. Now, I have a couple funny stories about this experiment. The first one is when I sent this off for publication, those of you who aren't in perception, we're notorious for using relatively few subjects. And the reason for that is we run hundreds, maybe thousands of trials on an individual subject. And so in the first version of this experiment, I sent it off to the journal and had 2 subjects. And the editor wrote back and said, I'm a little concerned about the number of subjects. And I read this and I go, shit, I'm in trouble. And he said, if you run another one, I'll be okay. So 2 wasn't enough, but 3 was fine. You'd never get away with that in social psychology. So the moral of the story is you really can use that information. Now I have another story to tell about this. About that time, there was a company in Connecticut called Ship Analytics. And what they do is, this is a totally relevant story to the cognitive engineers in here. So what Ship Analytics does is they did simulations of tanker ships. There's a real problem with tankers because, you know, when you're in your car and you turn the wheel, what happens? The car turns. But if you're in a 500-ton, I don't know how much tankers weigh, but they weigh a lot. If you turn the wheel of a tanker, you might see something happen 15 minutes later because of all the inertia. So there's a lot of lag. And what they were trying to do in Ship Analytics was to train tanker captains to be able to predict so they wouldn't crash the tankers into the dock because they didn't put on the brakes or turn soon enough to make this happen. And when this company heard that we were doing research on judgments of time to contact and movement, and so they were interested to see if we had anything to offer them. And so they were in, and I was given this sales pitch of, I have just the solution to your problem, and I laid out the theory behind time to contact and how you could measure it. And I said, not only that, if you come up to my lab, I'll give you a simulation, show you what it looks like right now. So I bring them all up to my lab, and I said, okay, how far away is the dock from the tanker? And I typed that parameter in my program. And I said, and how fast is the tanker moving? And I typed that parameter into my program. And then I said, all right, here it is, guys. And I hit the return key. Absolutely nothing happened on the screen because the distance was sufficiently long and the speed of the tanker was sufficiently small that there was no detectable motion at that distance. And my response was, well, never mind. My theory that I'd spent a half hour trying to sell them obviously wasn't going to work at all. The moral of the story is there are limits on what we can see, right? So in order for this to work, you have to be able to perceive the motion. And there are some situations, like a tanker pilot, where there isn't any optical motion to work with, and you have to do other things in order to do that. It's still a big problem of tanker captains crashing into docks. Navigation of those things is not an easy task to do. All right, let's move on to one more problem, and then I'll probably let you out early today. How many of you play baseball? What position do you play?
Third pitch.
Third and pitcher. What position do you play?
Center field.
Center field. You're the guy I want to talk to. Okay. What do you have to decide when you're in center field and a fly ball's going up?
Do I step back or step forward?
And how do you make that decision?
It's easier when it's hit at an angle.
That's true.
Default, so my default baseball training would say always, if you're in doubt, take one step back first before making a decision. But it's just instinct about, I don't know.
All right, I'm going to give you a theory of how you do that.
Go ahead.
And then I'm going to show you it's total bullshit. Well, actually, I'll claim that it's total bullshit, but then I'll show you an experiment by one of my best friends who says that's what people do, but I disagree with him on it. So how's the outfielder know where to go? Before I do this, are you familiar with this play?
Yeah.
Tell me about it.
It's an incredible over the shoulder catch right at the wall. I think.
Who did it?
Willie Mays.
All right. I think, we'll look at this film carefully, it is the luckiest catch in baseball history. But we can decide after we see the film. But it's often credited as the best defensive play in the history of baseball. So just to set the stage, it's the sixth game of the World Series. The San Francisco Giants versus the Cleveland Indians. Can you believe that? And the Indians are leading. It's 2-1. Guy gets up to the plate, hits this towering fly ball that everybody on the base passage just run as fast as they can because they know nobody's going to catch this thing. And that leads us to this.
And participated in 4 World Series. His catch of Vic Wertz's drive in the '54 series remains one of baseball's most memorable moments. Mays was elected to the Baseball Hall of Fame in 1979.
Let me play this again. I want you to look at where he's looking, right? So he's running full tilt this way. He doesn't put his head back. He's got his arms out like this, and the ball falls right in his glove. Is that a lucky catch?
Yeah, it's very lucky. Yeah.
Watch it again.
And participated in 4 World Series. His catch of Vic Wertz's drive in the '54 series remains one of baseball's most memorable moments. Mays was elected to the Baseball Hall of Fame in 1979.
Now, what's not shown in this film, it may be the best defensive play. So as soon as he catches this thing, he immediately turns on a dime and throws out the runner at second base before he can get back to the base. And that turned the game around, and the San Francisco Giants won the World Series, and the Cleveland Indians did not. So the question is, how can you do that? And so here's a theory about how you might do it. So this is not a very good figure. I apologize in advance for it. But consider this variable alpha. So suppose the ball is up there, like so, and that's the ground there. So the angle between your view of the ball and the ground is alpha. And beta is the angle from where the ball is projected down on the ground to home plate. So here's the deal. Now this is a model that I thought I had developed. So this is from a paper that I wrote in '81. It was actually developed earlier by a physicist, a guy by the name of Chapman, that I had never heard of. So he did it a decade before I did. But here's the idea. So let's suppose, this makes a number of assumptions that are clearly wrong. So it assumes that the ball travels in a parabolic arc, which is what a ball would do if it was traveling in a vacuum. But a ball traveling in air doesn't do that. So let's consider two cases. So now imagine now I've got a projection screen that I'm looking at the trajectory of the ball. So I'm looking at a ball through a window. And this is the observer. And if the ball is going to land at my eye, like so, the motion of the projection in the window will be a constant velocity. So if the ball is going to hit me in the head, its projection in the window will be a constant velocity. If the ball is going to land behind me, its projection in the window will be accelerating. So while it's going, it's actually accelerating while it goes up. And if it's going to land in front of me, it will be decelerating. So one way you could make that judgment is you look at the ball and you decide, is the optical projection accelerating, which means I got to go back, or is it decelerating, which means I have to charge it? Now there's another model. It's called the linear optical trajectory model, which I never really got because it doesn't actually catch the ball. It just keeps you on the same line that the ball is moving in. And the idea here is what you want to do is make the ratio of alpha to beta constant. So remember, alpha is the angle between the ball and the ground, and beta is the angle between the ball and home plate. So this is an experiment I did. You can tell this is the early 80s. This is pretty primitive computer graphics. So it just a dotted square that as it moved up and would expand, and what the observer had to do was to judge, I think they had to judge, will it hit me or will it land in front of me? And what we did is we measured the difference in landing distance. So on some trials it would hit you, and on other trials it would land some distance in front of you, and that was the independent variable that we measured. And so we could get distances of 10 feet, 20 feet, 30 feet, etc. Threshold here is about 10 feet. So subjects can do this task. They can get within about 10 feet. If it's less than 10 feet, then their performance drops. But we did a couple of other manipulations here. So one of them, the key thing about this model, it's very flexible in general. So it doesn't depend on the size of the ball. So let's suppose that you're standing in the outfield and somebody could throw a basketball at you, a golf ball, a softball, a hard ball, or a medicine ball. And you don't know which is which. If you were using optical acceleration, that shouldn't matter in the slightest, because it doesn't depend on the size of the ball. It also doesn't depend on the acceleration due to gravity. All right, so let's say that you catch a ball on Earth, where there's a particular fixed gravity, and then you fly to the moon and do the same thing. So you think you'd be able to judge a fly ball on the moon?
No idea.
Gravity's much less, the ball will go much farther.
Yeah.
But that optical acceleration model will work just fine. If you're using optical acceleration, then you should be able to judge whether the ball's going to go over your head or land on the moon. So one of the conditions I ran, whereas we varied the size of this thing and the acceleration on every trial. So it's like some trials you're on the moon, some trials you're on Jupiter, some trials you're on Earth. Sometimes the ball's a basketball, sometimes the ball's a golf ball. And performance took a big hit when you did that. Now that's not consistent with the optical acceleration model. And then finally we ran a condition where all you had was a single point. Now again, the optical acceleration model should work just fine in that case. Subjects are horrible. They can't do it at all. All of which suggested to me that whatever subjects are doing, they're not using optical acceleration. And the other evidence to support this, if you measure people's sensitivity to optical acceleration, it's really crappy. It's really crappy. We're very sensitive to optical velocities. We can discriminate very small differences, but we're not at all sensitive to optical accelerations. And in fact, that's a really hard experiment to do because acceleration gets confounded with velocity if you see the movement for any duration of time. So 1981, conclusion is whatever we're doing, it's not optical acceleration. And these are the two manipulations that led to that conclusion, plus a lot of other stuff on sensitivity to acceleration, et cetera. So the literature on this is sort of split into two communities. There's one group that comes from basic vision who knows about the acceleration research and says, no, people aren't doing that. And there's another one that comes from sports psychology that do their experiments a little differently. So what they typically do is hit baseballs, have outfielders catch them, and then they correlate the performance with this model. Now this is a subtle question I'm going to ask you. Can anybody see a problem with that strategy? The problem is any model that will actually catch the ball, if you catch it, will produce a high correlation. And there are a bunch of models that can catch the ball. And the people who are doing sports psychology, the only one they were considering is this optical velocity stuff. Okay, so that brings us to another experiment by Bill Warren in the, well, actually it's several other people and Warren. This is his laboratory at Brown University. It's this old chem lab. It's a wonderful laboratory. It's an old chem lab, and what they did is they put sensors in the ceiling, and so observers wear these trackers on their joints, which the sensors can pick up, and they're wearing a head-mounted visual display in which they can create false environments. So we hear a lot about this lab the rest of the day and next time of what you can do in a really nice, large-scale VR situation. How many of you have been in virtual reality before? What's the context?
Like video games?
Video games. Imagine one, though, where you can move around, like in a space like this room, in full-blown virtual reality. I don't know if the video games count, because they're not really responding to your movement. So for real virtual reality, you need a motion tracker, so as you move, the world moves with you. Now the problem with that is those trackers are hard to do. They need almost instant response time, because if there's any kind of lag in your motion and what you're seeing, it really screws up your performance. How about you? What's the context of your VR experience?
It was video games too. It was like with the Vive, though, if you're familiar with that headset. So, like, it's pretty realistic and there's not a lot of lag, and you have like a pretty small confined area, though, which is like.
Okay. What is it? The Oculus they use? Is that what it's called?
Yeah,
That
there's a couple different ones. The Oculus is one, and then the Vive is like one that's its competitor. I'm pretty sure. Yeah, HTC. Yeah.
Yeah, I have one in my lab. I haven't used it in about 15 years. It's probably not calibrated anymore. I visited Bill, and he had a demo that he does for everybody where you're in VR, right, and you're walking around. Again, the space here, bigger than this room, is the VR space. And so he puts you in this room, and there's this big pit. And so you walk up to the pit, and then the grad students say, well, you know, you can walk over it. And so I took a step out, and now I'm like, what is it, Roadrunner when he walks over the cliff and he stays up there for a while. And so I'm going, this is really weird, right? Because I'm standing on top of this pit, and then some graduate student in the back hits a button, and down I go. Now, of course, I'm in VR. I'm not really falling. But nonetheless, I landed, you know, like so. It's very convincing. I did a similar thing in my lab where you go up in an elevator, and when you get up near the top, the floor starts to shrink and then goes away. And as soon as the floor goes to nothing, then you fall down the shaft of the elevator. And hey, if you have a VR setup, that's what you do. So anyway, here it is in the Venn lab, and here is the head-mounted display, and here's an example of they spent a year building environments for this thing. So this is what you see when you're inside the lab. We'll talk more about this next time in another experiment. How many of you have played the game Portal? I see one enthusiastic. Just one of you? Okay, I'll tell you more about Portal next week. So this is Fink, Fu, and Warren, and they wanted to revisit this idea of whether you use optical acceleration. Now, before I tell you this story, I got to tell you, Bill Warren is one of my best friends. Every year at the Vision Conference, we rent a house together. He took courses from me when I was a postdoc. But he didn't cite my work when he published this on this. I will get back to that in a second. He was unbelievably embarrassed by this. I try not to razz him too much. So here's the idea. What he's going to do is he's going to have subjects try to catch balls in VR. All right, so you're in VR. There's no real balls. It's a simulated ball. And because it's in VR, you can play games with the trajectories, just like I did on my desktop thing 3 decades earlier. And so you use two kinds of trajectories. So a normal trajectory where the ball moves in a parabolic arc. Again, I should stress again, that's not a normal trajectory unless you were in zero gravity. I'm sorry, unless you were in a vacuum. And then he also did distorted perturbed trajectories where they cut. Instead of moving in an arc like so, it would go straight down like so. And so they divide the trials into these cases. The subjects would see a ball traveling in VR, and then they would try to catch it. And so here's what that looks like from, if you're watching the observer participate in this. It really looks like somebody trying to catch a ball. And here's what it looks like if you're the participant. I don't think he had any trouble getting volunteers to do this experiment. I think this was a fun experiment to do. Though again, the idea, for me anyway, running around in VR does not strike me as, at least at my advanced age, I don't think I would try it. So here's where the positions of the ball landing are. Remember, the blue lines, do I have that right? Yeah, the blue lines are the normal trajectories, like so, and the red lines are the perturbed trajectories. And the data are a little noisier for the perturbed trajectories, but they catching the ball in both conditions. So they're able to do it with the perturbed trajectories. Now, the key thing here in their analysis is the alternative model, the only alternative model that he knew about, was the idea, if you look at the relationship between tan alpha, remember alpha is the angle between the ground and the ball, and beta is the angle between the ball and home plate. And if you look at the ratio, if you look at the perturbed trials, so if you look at the regular trials, this is a straight line in the subject's behavior. But if you look at the perturbed trials, it moves in a straight line and then the slope of that line changes. And alpha does the same thing. So in the regular trials, it does this, and on the perturbed trials, it does that. So if you look at tan beta over tan alpha, so this is the second model I told you about. You want to keep that constant. So the perturbed trials, that model doesn't work at all. It works okay for the normal ones, but it doesn't work for the perturbed trials. All right, so he's considering two models. One model says the perturbed trials shouldn't matter, and they don't seem to matter all that much. The second model says the perturbed trials shouldn't matter, but they matter a lot for the second model. And so Fink, Fu, and Warren concluded from that we actually used the nulling of optical acceleration in order to judge fly balls. For which I sent him an email and said, Bill, you're my best friend. Why didn't you cite my paper? And he wrote me back, I'm embarrassed, about 10 times in a row. And we've agreed sometime we'll go back and do this experiment together. What I want to do is, instead of the manipulation he did to measure, is to change the size and acceleration constant. And if they really are using optical acceleration, then that shouldn't make a difference. Now, in fairness, his method is elegant, it's beautiful, it made psych science. I mean, if I'd reviewed it, I would have been very positive about it. You know, mine was crude, crummy graphics, not even for desktop VR standards. It was in 1981, for Christ's sake. However, the manipulation I did was a much more powerful test of the model than the one he did. So I would like to see somebody go back, redo that experiment, vary the size and acceleration of the ball, and see what happens. Not going to be me, because I don't have that lab, but maybe I can talk Warren into doing it sometime before he retires. So I'll let you go for the weekend. We have our last lecture next Tuesday, folks. And so we'll talk a little bit more about visual navigation, and then our final, the last exam is not a final exam. The last exam just covers the material for this section, will be the following Tuesday. And the Tuesday after that, I will be in Naples, Florida.